Hello and welcome to Random Intercept Models, Part 2. Last week we talked about the beginning of random intercept models. We introduced the concept, or continued the introduction of the concept since we began the process of learning about random intercepts when we talked about variance components models. And we began adding variables to our models. We talked about some of the assumptions. Today we're going to use some of those assumptions. So we're going to use in particular, we're going to discuss the endogeneity or exogeneity assumption, rather the idea that the zetas are uncorrelated with all of the x's after we've conditioned on the x's, and then what we can do with them. And we began that last week by exploring the between and within, but we're going to spend some more time thinking about that in more detail. And then we're going to think about interactions today. And we're going to finish with some discussion of dealing with residuals and looking at the residuals, both the zetas as residuals and the epsilons as residuals too, and doing the kind of interrogation of them that you did in your first class, regression class, where you looked at the residuals and tried to get a sense of what's going on with them, since the assumptions of that are the same as the first one, except now we have two parts. We have the level 2 and the level 1. So if you recall from last week, we were predicting birth weights, and the primary variable of interest was smoking and how smoking affects birth. And what we see here is that as you move from a 0 to a 1, from non-smoking to smoking, the birth weight of a child goes down 218 grams. Now, this conflates two different forms of smoking. It conflates both the between and the within, and in doing so, it's technically a weighted average of the between and within, and there's multiple implications of that. One, we're essentially making the assumption that the between and within are the same, and that this weighted average captures what we're interested in. The second thing is that when we estimate the zetas, right? So this is the residual. This is the variance of the zetas down here. That we're assuming, and if you recall from last week, we're assuming that those zetas are uncorrelated with all of these x's. And if there's a difference between the between and the within effect, it may be that the between effect represents a correlation between the zetas and this x term that we are either going to have to adjust for explicitly or figure out some other way of dealing with. And so we want to talk about those issues today. All right. So we've extracted this coefficient right here and brought it here for the reason of talking about it in the context of both the between and within. So if we think about just the between model here, the between model is the idea that the average of all a mother's births, and I know that we're talking about mothers here because J is the representative term for mothers, the subscript for mothers, and because there's just a dot here, there's no I, and the bar here tells me it's an average. So this is the average of all mothers, of each mother's births. Not average over all mothers, but each mother, each J, which is a mother, has an average birth, and we're going to predict that as a function of a standard intercept, as well as would be our smoking term here. So this would be the average of her smoke, of how much, whether she smoked or did not smoke during a birth. So if she didn't smoke at all, it would be a 0. If she smoked every birth, it would be a 1. If she smoked 1 out of 2, it would be 0.5. And if she smoked 1 out of 3, it'd be 0.33. If she smoked 2 out of 3, it'd be 0.66. You get the point, right? So this represents the average of how much she smoked in her birth, etc. for all the variables. We still have a random intercept in these models, and we also have an average of the epsilons here. So this represents the between model for mothers. So we're just comparing across mothers, and I know that because we just have J subscripts here. There's no I, so there's no within mother effect. There's only between mother effects, and we can estimate that in Stata using between regressions, and that's XT-reg. So if we go to sorry, let me get rid of this. I've failed several times at this lecture so far today, so on like the fourth attempt here. So we've got xtreg, and so we call up the smoking data. We do xtset to let Stata know that we've got data nested in momID, and then we run the xtreg with the BE option as opposed to the FE option at the end, and that gives us the between effect, and we get the coefficients that we just found. And so this represents the difference between mothers who smoked never and smoked every time, right? So it's a 1 unit change in X is this corresponding coefficient change in Y. This is the decrease in birth weight, which is our Y variable. 1 to 0 is mothers that never smoke to mothers that always smoke for all of their births. And so we can estimate the between model. So that's of use, right? So we're able to isolate those effects. We can also, and we've developed the skills necessary to also estimate this within effect, and this would be our fixed effects model, which we've estimated before. So this represents the difference between the average within mother and the individual observation. So we're looking at the deviation within mother. Here's the deviation in smoking within mother. Here's the deviation within mother for some other variable. We can do this for all the variables. Obviously, we can only do that for variables that have an I. They have to vary within mother in order to be interrogated here. And then we get this error term, which represents the difference. This is our fixed effects model that we've seen before. And of course, we can estimate that using xtreg as well. You will note that we are not able to estimate the non-changing variables as we knew before. These things do not get estimated because there's no variation within mother. So this represents the change within mother as a mother moves from non-smoking to smoking, that she would expect to see a decrease in births by 104 grams. Now, what's the difference between the within and the between model here? Well, the difference is that the fact that a mother smokes tells us something about the mother itself that's separate from the effect of smoking. And the within effect, there might be lasting effects of smoking. There might be persistent effects of smoking that are attached now to the mother, as opposed to the actual physical effect of smoking in the moment, right? So the moment effect, that's the within effect. The effect that's attached to the mother, that's the between effect. But smoking might tell us something about the mother in general, right? The mothers that smoke might do other things. You'll notice that we don't have drinking here. How much does a mother drink? Well, smoking is associated with drinking. Smoking is probably associated with other substance use. Smoking may be associated with poor diet or other health-related activities, right? People that don't smoke are probably more attuned to their health than people that do smoke. And so smoking is not just a marker for the physical activity of smoking itself, but is also a marker for a whole host of confounding effects that we don't see in the within effect because that is controlling for it, but we do see in the between effect. So when we model the between effect of mothers, we pick up those elements that differ between mothers that smoking is as an indicator for. When we look at the within effect, we've removed all of those by controlling for those factors. So this is just the effect as a mother moves between smoking and non-smoking. The fact that there is this confounding effect of mothers that is associated with smoking is our level 2 endogeneity problem, caused by a level 1 covariate. So smoking varies within mother, so it is a level 1 covariate. But it is correlated with the level 2 covariate for reasons that are not just adjusted for here. And you can see that effect here in this picture. So as we talked about before, our zetas cannot be correlated with our x variables after conditioning on the x variable. So after we include the x variables, there can't be additional things that are associated with it. There can't be additional confounding that links these x variables to our zeta terms. That would be our level 2 endogeneity problem. Level 2 being the zetas. The endogeneity is caused by a level 1 variable. So there's a little bit of confusion here. We have a level 1 variable causing a level 2 endogeneity problem. And you can see that here. These black dots represent the zetas. And you can see those zetas are correlated with our x terms here, the x term running along here. And you can see that by this line, right? So they fall nicely along this line here. And that suggests that there is an association between the mother intercepts, the intercepts for mothers, and in this case, we're talking about smoking. So mothers that smoke more have lower birth weight. It would work in the opposite direction. Right? Our line would go this way, not this way, but you get the point, that there's an association between our zeta terms and our x. There's a correlation, and that's a problem. So we benefit in a random coefficients model, in a random intercepts model, by being able to model both the within and between, but there's risks associated with it. We're able to do that because we make certain assumptions, and one of those assumptions is that the zetas are uncorrelated with the x's after conditioning on the x's. After we include the x's, the zetas need to be a random distribution, not associated with other terms in the model. That's not true of our fixed effects models. Our fixed effects models, we don't care about that. We control for all of those level 2 covariates by adjusting for mothers, right? So all of the things that stay static within mothers, I am a person that cares about my health, or I am a person that doesn't care about my, I don't want to say doesn't care about my health, but doesn't care for my health. So those things that how healthy I am as a person are marked by smoking, correlated with smoking, correlated with health, with outcomes for births, and thus correlated with my mother intercepts, but not totally controlled for by smoking. So the random intercept model, those coefficients, because they are weighted averages of the between and the within, those between effects can be a source of that level 2 endogeneity, because they end up in the weighted average, and they bias our coefficient estimates and our standard errors in particular. The random intercept model benefits by combining the between and within because there's more information, and statistically we call that efficiency. So it's more efficient at using the available information because it grabs both the between and the within information and includes it in the model. The problem is some of that information may induce this bias that we're worried about. So because of this combination, we have to be careful of this level 2 endogeneity. Again, fixed effects do not have this problem. Only random intercept models have this problem. So how do we deal with this problem? Well, one way is we can interrogate this and explicitly model the between and within effects. By explicitly modeling the within effect of mothers, we can capture that variance. If we know what variables are causing the problem, we can identify it and explicitly model it. And we can do it by separating out and essentially creating a mini fixed effects model within. We control for the static effects of mothers and smoking, the consequence of them smoking, all those health effects, that gets captured by this variable here. And then we separate out the change within mother in terms of this variable here. So in cases where there's a difference between this and this, we can model that explicitly, control for the endogeneity problem by including this term, and understand the within mother effect by including this term. And you can see here that we simply do that by subtracting the group mean, not the grand mean, the group mean, the mean for each mother from the individual observation, and including that in the model, and then including the group mean, the mother mean, in the model as well. Now, last week somebody had asked about whether these two are likely to be correlated, and probably not. They're probably not correlated, and it's okay that they're correlated. Like as long as they're not correlated at 100%, and they should not be, that we're okay, right? So as long as we don't run into multicollinearity problems with really high correlations, we're okay. And there's no reason to believe these would be particularly highly correlated. So we did that last week, and you'll recall that we got a coefficient for the within mother effect and the coefficient for the between mother effect. So what the between mother is interpreted as is a difference between a mother that moves from no smoking at any of her births to 100% smoking at all of her births. You would expect a 289 gram decrease in births as you move from one mother to another. Now, this variable includes all of those problems that we were discussing. Mothers that smoke probably drink more. Mothers that smoke probably engage in other behaviors that would not be beneficial for the weight of the baby in terms of the weight of the baby. So those things are adjusted for by including an X variable, just like we control for anything, right? So we've addressed the endogeneity problem by including it. And then this isolates the effect as a mother moves from smoking from non-smoking to smoking. What you would expect is a 104 gram decrease in the birth of the baby. These two are combined in a weighted average, which is why the coefficient when we don't include it is between these. When we ignore this endogeneity problem as evidenced by this, right? So we can explicitly model these. And that explicit modeling allows us to figure out what's going on, and it allows us to adjust for the level 2 endogeneity of level 1 covariate. So this only works when our covariates vary within mother, not just between mothers. The between mother covariates, we don't really have a technique for that yet. We will later, but we don't yet. So I might not be interested in these, but only interested in knowing whether my random coefficients my random intercept model effectively models it. And I can do that by testing whether these coefficients are the same, right? If it's a weighted average and this within effect and this between effect are essentially the same, then I don't need to model them separately. I don't have endogeneity, or I likely don't have endogeneity problems here. And I can do that by using LinCom, which is linear combination. And I just say variable 1 after you run the model, and all the applications have it. R has ways to do this. SAS has ways to do this. So you take your coefficient from the model and you subtract it from another coefficient in the model, and you can tell whether these coefficients are the same or not. The assumption is that they are 0. And what we find here is that there is a statistically significant difference between these coefficients. I will note that it's about 185 gram difference, right? So the between effect is about 185 grams more than the within effect. And you can see that when you look at the covariates, right? That's 185 essentially, right? As you subtract those two out. LinCom, you can subtract them out yourself, but LinCom gives you these nice confidence intervals and p-values, so you can figure out whether that's statistically significant or not. Okay, so that's one way, is we can use the between and the within models that we've already developed and isolate the effect. Now, if you're just interested in understanding whether your covariates have this problem, this difference between the within and between problem, but you're not interested in really interrogating those differences, you can check pretty simply by using another formulation of the same version, and that is by so in this formulation, we have the within variable, which is just our smoking variable. No, we don't subtract it from the group mean. We just include the smoking variable, right? So this is smoking. And then we use the group mean centered variable here. I'm sorry, we use the group mean here. And what happens when you include both the group mean and the individual variables is you essentially create a difference variable. And you can see that when we run it, right? So this is the group mean variable that we just got through calculating the group mean. And when we look at this, this is our within effect, right, which we saw before. And this is our within minus between effect. And you notice it was 185 before. It's a little different here. It's 183, but that's really close. So we're able, just by including the mean and not the deviation, but the variable itself, we can also isolate the within effect and look at the difference between the within and between effect and statistically test it embedded in the model. And here we see that we have a statistically significant effect for smoking. So there's a difference in the between and within effect for smoking. There's no difference for male births. And so the number of male births is not related in terms of between mother effect. It's all whether the birth is male or not male that matters, and that's not terribly surprising. The maternal age and the difference between mother's age does matter, and that's also not surprising. The absolute value of a mother's age in terms of the overall of her births matters in addition to the difference between a mother's age at a point in time and the mean of the mother's age. So older mothers there's a U-shaped curve here. So younger mothers have lower birth weights. Older mothers, and you can see that, and I think that this is mostly this effect as you go up in age. I'm sorry, this is the opposite effect. This is the other part. So there's a U effect of age. As you're older, there's an N effect. As you're older, birth weights go down, and younger, particularly teenagers, have lower birth weights, and you sort of peak in the middle or in the highest level of fecundity, which it tends to be in the 20s and early 30s. So what this says is that as you compare a mother that is 1 year older than another mother, you would expect an 18-year decrease. As you move, adjusting for this, within mothers, each added year of age increases the birth, and you can sort of see that effect here by the flip of the sign. So both of those are true, but we have this additional confounding. So our zetas are confounded with the mean mother age, and we have to adjust for that. We have to figure out a way to adjust for that. You'll note that these other variables are not really. So, these variables aren't, this variable isn't. You'll notice these variables don't vary, so we're not really interrogating them here. But none of these other variables are statistically significant. So these variables don't have this confounding problem, and they also don't have a difference between and within. We can just estimate one effect, and the weighted average is going to work well for us. Whereas smoking and maternal age, we have to model explicitly, and we can. We've developed the tools for that. So let's just take a step back and think about what we're saying here. We're saying the problem comes when we have zetas correlated with x's. And the zetas in this context are the average birth of a mother after adjusting for all of the x's. So all of the effects of the x's are taken out. The stuff that is left represents all of the uncontrolled for uncontrolled for stuff, right? So because we didn't control for drinking. So does a mother drink? Does she have a lot? Is she eating eating a diet of kale and berries with a little bit of protein mixed in, or is she eating Five Guys every meal, right? So all of those health behaviors that are correlated with smoking but not explicitly adjusted for in our model end up popping into this, and this correlation between smoking and the zetas ends up being that level 2 endogeneity problem of level 1 covariates, right? So it's a level 2 endogeneity problem because of the zeta. That's our level 2 variable, but we've only been able to interrogate this in level 1 variables that vary within mother, and we do that by separating the within and between mother effects and separately estimating them and testing whether they're the same. That tells us whether the multi-level estimation, the random intercept estimation, which is a weighted average of the two, is an effective tool for estimating that coefficient. And if we do identify problems in variables that we have, we can include them in the model and thus adjust for them. Now, this is not magic, and there are still problems. One is we still cannot deal with level 2 endogeneity of level 2 variables. So covariates that only vary, and we had some in the model, right? We had high school grad, we had some college, we had college grad, we had married, we had black. I don't know why married doesn't vary. Suppose all of these mothers were either married or not married. Maybe it was back in the day before divorce was possible. Anywho, in this data set, these don't vary. So these are our level 2 variables that only vary by j. There's no I for any of these. So we can't interrogate those, and any endogeneity there is still a problem for us. And our level 1 endogeneity with level 2 variables or level 1 variables is also still a potential problem. So we still have issues making sure our variables are effectively, that our model is effectively estimated correctly. Now, I will note here that this problem is solved in fixed effects because we get rid of this stuff. This problem is solved in fixed effects because we get rid of it. This problem is still a problem in fixed effects models. So this is the problem that we talked about before, that varying variables are not adjusted for. Only the non-varying variables are adjusted for in fixed effects. So fixed effects still have this problem right here. But they solve for these effects. So when thinking about whether to use random or fixed effects, we can think of a couple of different things. One, we can think about, do our models effectively treat the, do our models effectively deal with the between and within variance? And for those variables that vary within cluster, we can ask that question by estimating it. So let's go and look how I ran that model, because there's something that I want to touch on here first. So first of all, this is how we got the variable, and we separated the deviation and the mean mother. So this is the mean across mothers, and by sort mom ID tells me that I'm going to do this command for every mother. So within mother, I'm going to get the mean of smoking, and that's how I construct that. And then we estimated that model. I don't want to estimate it again because it'll take a little time. Then we've got the lincom. But the thing I did want to show you for the second model that we ran is I was able to construct a variable, all of these mean variables, so mean smoking I already created, but mean male, mean mother's age, etc., by running a loop. And as I've told you, I've mentioned this before, one of the programming things you want to learn how to do in SAS, these are arrays. There's also loops in SAS, but arrays are one primary tool to do this. R has a ton of different loops for a variety, but you can use a variety of different loops. But loops are a really essential programming tool. So instead of having to write this command for each of these variables, male, these different guys, right? I don't have to do that. All I have to do is say for each var, and now var becomes a marker. It's the index term for each var of var list, and that just tells Stata that there's a bunch of variables coming. And I put male age. Because I have 1, 2, 3, I can just put the first part of it, right, and then leave off the second part, and it'll leave that out. And then no visit, and then whether they had a prenatal visit. That again here, because I have 2, 3, I could just put the stem here with that. It'll run over and it will do that. So what will happen here is for each var of var list, blah, blah, it'll say, okay, by sort mom ID, egen, create mean first variable, male. And so it plops male in there. And then it says var male. So it plops male in there, right? So I'm just doing this command up here over each of these variables, and it just runs through all of them. So it's a very effective way of programming lots of stuff. And I will tell you, loops, you want to learn how to use them. It takes a little bit of cognitive energy to figure out how to use them, but once you do, you will be using loops all the time. It is a really, really effective programming tool. So strongly advise you spend some time learning how to do loops in your respected applications. And then we ran that model, which we saw earlier. I can show you again. Well, I didn't actually run it. Let's see, blah, blah, blah. And then, here we go. It does the loop-de-loop. And then it runs the estimation. Okay. So, I really just wanted to take that detour and talk about loops. Let's go back to thinking about random intercept models, and we have essentially finished the between and within piece for now. As I told you, this whole class is about between and within, but the take-home message here is that we can separate the between and within effects, and by separating the between and within effects, we can not only identify endogeneity problems, but when necessary, we can control for them. There are many, but another benefit of having both the between and within variables available is that we can run interactions between those two levels, which is a little bit more complicated in fixed effects models since we've gotten rid of all of the between effects and we're only left with the within effects. So if we have something that doesn't vary over time, or over a unit, and we want to run an interaction with it, we have a harder time doing that with the fixed effects approach. But with the random intercept approach, we can do that, and it's a real benefit. So the good news is that these cross-level interactions, the level 1, level 2 interactions, are just interactions, and you interpret them as you would any interaction, but they're a powerful way to interrogate your data. And here I'm going to highlight the fact that we have been talking about group mean centering so far. Here we're going to do grand mean centering, which is just centering over the mean of all of the things at level 2, because we're going to want to see where the data is most common. We're going to want to see at the average of the data, and that's what centering allows us to do is move where the zero term is to the center, and that's useful from an interpretation point of view. All right, so I'm now using the data from the plain language book, if you have that. And what we're going to do is we're going to look at the data that is the schools data. So this is the Australian schools data, and we're predicting reading scores. And we're going to predict reading scores. We're going to start by running an interaction where we're interested in the question, do girls do better in schools where there are more girls? So in order to figure out if there are more girls in schools, we have a variable called PC girls, and that's the percentage of girls that are in a school. So that, it can be 40% or 80% or whatever. For a girls' school, it would be 100%. So girls, the percent of girls in a school is one variable. And then we have an estimate for girls and for female, right? And so what we want to know is, do girls do better in girls' schools, or does it not matter? And so we can ask questions about this interaction, right? So we have a level 2 variable that doesn't vary within schools. If we look at the data itself, right? So we have our reading scores, which vary within school, right? So these are all the reading scores for girls in school, or everyone in school 1. But then we have the percent girls in that school. So there's 46% girls in this school. I know that we've switched schools because this now becomes 48%. So there's 48% of girls in this school. This school is an all boys school, right? This school has 48% girls. This is an all boys school. This school is an all girls school. This school has 48% girls, 47% girls. You get the point, right? So these don't vary within school, and we can interact this non-varying within school variable with a variable that varies within school. Let's see here, female varies within school, and that's a cross-level interaction. That is a level 2 to level 1 interaction term, and we can do that here. Now, in order to effectively interpret this, because otherwise, if we don't center this, what we're really asking, the point where we have the point where 0 is available, is where there are 0. So it'll be, what is the, so right where this variable is 0 is in a boys' school, which is not what we want, right? So when we interpret this, what we would interpret this coefficient as is we want it to be meaningful. We want the center to be meaningful. We want 0 to be meaningful. And so I'm just going to take the average across all schools and use that as the center of this variable, and we're going to call it center girls. So we're just centering this variable. But you will note that if I were to just do that without this term, without picking just one, I would get the weighted average. So schools that have more students would contribute more information. Schools with less students would contribute less information, and I don't want that. So I'm going to create a variable called just one that tags one of these observations, and then estimate a variable that is, I'm going to estimate the mean of that, right? So the mean is 49, 40, it's almost 50, which is good. And then I'm going to use that mean, which I call by calling it R mean, and mean center it. So now I have a variable where 0 is 50%. So this would be what, 47% something, 46%. Let's see, one that's 48%, that's going to be a little lower, right? And then one that is, let's see, let's find something where, so this is 1, right? So this is going to be like 0.5%. So we've taken this variable and we've just centered it. But we did it by selecting just one person because this is the same within all schools. So we just needed that. All right, so here we go. We're going to estimate this model and interpret the coefficients. Let's do that. All righty, so here we are. Now, female is 1. Male is 0. So this is right here. This is the expected reading score for a male in a school with average, and this is 0 because that's 0. The coefficient for female is 0. This is 0 at the average of all schools' gender balance. So that's where schools are what, 49% female? And this is 0, right? So this is the score for boys at a school with the average number of females. All right. If we want to calculate what the score for females is, we can run through that too. So it's this plus this, right? So we can estimate that. So that's our intercept, and then we add in our coefficient for females, right? And at the average school, so this is 0 at the mean. So at the average, it's 0 times the coefficient, and this is why we did that, so that this term is meaningful, and that this is also 0 at the center, right? Because it's 1 for females times 0 for centered, right? Because that's at the center, times the coefficient value, right? And so this is really just these two terms. But the reason why we center it is because it makes the interpretation more meaningful, that this doesn't move, right? This doesn't, we know what this coefficient means because it's at the average school, as opposed to an all-boys school, which is a meaningless term for us, which is what it would be if we were using the formerly oriented percent girls score. Okay, so, but we might be interested in what happens if it goes up, right? Because this is statistically significant. This interaction term is statistically significant. And we might want to ask this question as we move up in the percent of girls in a school, what is the performance for girls in schools? And we can keep doing this, right? And keep calculating this for each one. So let's just do that. Let's say we want a school with, let me copy this. Let's say we want a school that's 60% female. So that would be 0.1 for this variable, and it would be 0.1 for this, right? Because I'm saying 60%, the essentially 50%, it's 40, it'll be 60, 59%, whatever the mean is, right? So the mean is 49%. So that would be 59% would be 0.1 in this mean centered variable. So this variable and this variable are put in there. And so the expected score for a girl at a school that is 60% female is this term. Now, we might want to know whether these are statistically significant. We might want to know what the confidence intervals around those are, because we lose information in certain places. And in Stata and in R, there's an application called margins. The R one is a repeat of the Stata one. It's an attempt to get at the Stata one. SAS has PLM. I've talked to you guys about that. So there are ways that you can get these interactions. You can also do that with the estimate commands in SAS. But in Stata, it's called margins. And what I call so after estimating, it's a post-estimation command. So after running this model, I call margins, and then I say, I want to know this over, see here, we set it at 0.1, but what I want to know, starting with minus 0.5, so that would be a school that is, so minus 0.5 would be a boys' school, all the way up by 1 unit increments, by 0.1 unit increments, so 10 percentage points, up to the top one, which is 0.5. So that goes over the whole range, and I can get an estimate of each of those. This is not the easiest thing in the world to read. You have a key over here. So this is girls at an all girl. This is girls 1 at 1 will be a girl at an all boys school. And a girl at an all boys school would be expected to have a reading score of 0.09. So girls would do. A girl does not want to go to an all boys school if reading attainment is the issue that you're interested in. Incidentally, this is the score for a boy at an all boys school, because we have estimated the converse. Once we get up to, let's see, 0, so this is our centered one. And what is that? That is 6. Let's see, 0, 1, 6, right? So this is a girl at at a 50% girls school. You'll notice that term is this term right here, right? We calculated that. And that's right here. And so we can interpret, we can get the means, but we also get the p-values and the confidence intervals. So that's very useful. But as you know, I like pictures. I find this sort of hard to interpret. You know what I don't find hard to interpret is the picture. The picture is pretty straightforward. Here is the effect. You can see it crosses way down here. So really, boys, and you can see the confidence intervals, or the bands, the 95% confidence bands get bigger at the ends and smaller in the middle where we have more information. But basically, females are the red line, males are the blue line. Males do better at all boys schools when they're not distracted by girls. But as the number of girls go up in a school, boys do worse at reading. And by the time you get to an all-girls school, this poor boy can't pay attention to anything, and he is doing very poorly in reading. Whereas the girls have the opposite effect, although you'll notice a much less steep change as you move across that line. But you can see dramatically the interaction effect here between a level 2 variable and our level 1 variable. And the interaction is informative. It tells us something about the effect of gender and schools on gender in schools on individuals of different genders, and is very useful. So that was a level 1 covariate that is binary and a level 2 covariate that is continuous. We can also do this with a level 2 covariate. So if we look at student-teacher ratio and we just look at boys because there's actually no effect for girls. But with boys, if we look at the student-teacher ratio and then the POS variable, which you might recall from an earlier lecture, is the status of the parents of the parents' job. So this is the student effect. So this is how this is again grand mean centered. But this is the grand mean centering. So the middle is going to be the average socioeconomic status of a student's parent. This is a level 1 variable. And then this ratio is the ratio of students to teachers, which is obviously a school level variable, a level 2 variable. And we can run an interaction with this. Now we have to, when we do this interaction, what we see, and we can, so this is only within men. So that's the if males equals 0, if females equals 0. So that's only for boys. We can see that there is a statistically significant interaction. So here's the reading score for boys who have a average parents SES and an average score on teacher-student ratios. Right, and this would be 0 for each of those because those are at 0. But again, we might want to know how that changes over the range. At what is the interaction effect between socioeconomic status and student-teacher ratio on reading performance for boys? We can ask that question by doing the same kinds of things and getting our margins. Now, what we're going to do is we're going to turn this centered ratio into a set of tertiles. So we're gonna split it into 3s, and we do it by using these stata commands, and then we are going to estimate our margins command again. And here we're moving from the from negative 20 by 5-unit increments to 20 of the center variable. So the at and then over tertiles is going to just do it for one of each of these 3 groups. And you'll see it in a second. So this is a lot to pay attention to. I wouldn't necessarily spend my time interpreting this. I mean, if it were my research question, I would. But in this context, I'm not going to. What I'm going to do is point you to the graph, and we can see that interaction effect pretty clearly once we graph that. And so what this interpretation means, so here we have the dots are for schools with a low student-to-teacher ratio. The triangle is students with a high student-to-teacher ratio, and the triangles are the diamonds are in the middle. And if we look at this graph, what we see is that the effect of a parent's SES is moderated, and that's what this is a moderation analysis, by student-teacher ratio. Teacher-student ratio is what they call here, teacher-student ratio. And I say that it's moderated because I know that the slope of the high teacher-student ratio, so lots of teachers for each student, has the slope of socioeconomic status on reading is less steep than it is at schools that have a low teacher-student ratio. So few teachers for each student. So the effect of teachers, it's the opposite. We call it student-teacher ratio. So you have to flip the concept here. So students to teachers. Here it's teachers to students for whatever reason. So it's flipped in terms of concept. But you can see the interaction. You can see that it's not particularly strong, but you're able to at least have a pretty clear picture of it. So the margins command and these kinds of estimation tools give you a really important way of interrogating these interactions. And multi-level modeling allows you to ask these cross-level interactions. What's the effect of schools and school-level variables on individual student performance? That's not the kind of thing you can ask in a fixed effects model. So random effects models give us a really important tool set for asking questions about the effect of level 2 covariates on level 1 variables. Thinking about that endogeneity problem the whole time. All right. So as I mentioned before, and the last thing we're going to do is we're going to cover investigating residuals. And So we're going to switch back to smoking for this. As you know, we have two forms of residuals. We can think of this as a mean, right? But we can also think of this as a residual. And so we have our zetas and we have our epsilons. Now the epsilons we know how to get. We've always been able to get them. But the zetas, I just want to review how we get the zetas. We estimate the zetas because we don't get the zetas naturally, right? The zetas as a random effect are not directly estimated. We estimate the variance of the zetas, but we don't directly estimate the zetas. So we have to call for the estimation of the zetas. We can do that through maximum likelihood, or what I would recommend is empirical Bayes. Maximum likelihood with the student data would not be that bad because we have a lot of students in each school. So it would be a pretty effective tool for estimating it. And in the empirical Bayes and the maximum likelihood estimates would look very, very similar because there's a lot of data being brought to bear. But in cases where there's less data, for example, with the smoking, where we have maybe 2 bursts or maybe 3 bursts per mother, we don't have a lot of information to get our maximum likelihood estimate, which is just the mean of the mother, the group mean. So we want to borrow information from all of the means and our assumption about the distribution, which we assume that it's normally distributed with a mean 0. And so we can use those with the empirical Bayes methodology of estimating zetas. We can borrow that, and we can then interrogate the quality of these zetas and whether they're normally distributed, and then heteroscedasticity and other things as well. I will note that the empirical Bayes estimate uses the prior, which is the assumption that there's the estimated variance that we've estimated, and that the mean is 0, and that they'll be normally distributed. And so it borrows that information, combining it with the likelihood equation, which is the data itself, and then generates a posterior distribution from which you draw the zeta responses. Now, as I said before, if you have a lot of data, then the prior gets sort of washed out in the likelihood, but we'll talk more about Bayes at the end. I'll give you a little bit of a Bayes primer. The picture here, I think, conveys the information that we want. In a situation where there's lots of data, the Bayes estimate and this would be the maximum likelihood estimate will end up being very, very similar because there's a lot of data, and you know that by the peak. The peak is really high. When there's less data, this maximum likelihood estimate will get shrunk back to the mean 0, and so it'll be a little bit less. So the depending on how much data you have. So for the student example, it would look more like this. For the smoking example, it would look more like this. But these are generally considered more robust, better estimates of our zeta term, and the one that I would recommend that you use. And I think it's not just me. I think most people would recommend it. All right, there's some other pieces here. Shrinkage will increase when you have a small random intercept variance, i.e. the prior is more informative. It tells you more. If you have a large level 1 residual or uninformative data, the shrinkage will increase. Or if you have small cluster sizes, as we mentioned before, the shrinkage will increase. So the Bayes comes in handy when we have problems with the data, either small sample size or too much variability, or not a lot of variability, and the prior is really close, right? The prior tells us a lot of information. So those are all ways in which we get shrinkage. All right. So now, once we have this, we can start asking questions about our residuals. And I will note that this is no different than what you've done before. The techniques are the same. The difference between what you did in your first class for estimating the residuals and this class is you have 2 sets of residuals to interrogate. Now, we have the level 1 residuals, and I would note these are our zetas. And we have the level 2 residuals. These are epsilon ij's. The zetas and the epsilon ij's, when we're using Greek letters, those are theoretical constructs. Here we have actual observed values, and so we use R as opposed to epsilon and zeta. We calculate these using the same kinds of techniques that we did before. So I'm going to go back to the smoking data, and I'm going to estimate a pretty standard model. I'm not going to show it here because we don't need to see it again, but I'm just, smoking, and this is the base model that we used before. In Stata, R has ways of doing this. And I can share some. There's some applications, and I can share that with you guys. I found some good websites for that. And for the SAS people, I put in the Dropbox folder. There's the Dropbox folder that you guys created. I put an article on a macro that can be used in Mixed to get all of these. So we can produce the level 2 effects by asking for R effects. So that's our level 2 residual. I can get our level 1 residual by asking for RESES. That's just the residual term. I will note that right. So I can get, no, I'm sorry. Let me change that. To get the level 2 residuals, I can just do this, but I want the standardized residuals. So I need the SES of the random, I need the standard error of the random effect in order to calculate the standardized residuals, because Stata will not give me the standardized residuals for level 2. It will only give me the raw residuals, the zetas, but I want the standardized zetas because I want to compare standardized to standardized. So I get the SES, I generate I do this little mathy thing here where I take I calculate the standard error using the constant, using the variance. This is my random intercept variance, and then taking the standard and subtracting out the standard error variance and exponentiating that, and taking the square root of that. So you can see this in the Sophia Ray Hesketh book where the formula comes from, but I didn't get this. I just copied what she said. And then I divide my level 2 residual, which is the zeta term, by that standard error, right? So I just divide by that, and that gives me the standardized residual. And then for the level 1 residual, I can just say predict level 1 are standardized residuals. Now, you don't need standardized residuals. You don't have to go through this. We could just compare this to the non-standardized level 1 residual, but I like standardized residuals, and I think there's a value in looking at them. So I'm just going to do that mathy stuff. And again, we stand on the shoulders of giants. So this formula right here, you could figure out how to do in whatever application you use. But suffice it to say, there's books for this kind of stuff, right? This now is how you would investigate it, right? So I can look at the histogram of level 1, and this is my histogram. So these are standardized level 1 residuals. You can see that there's some tail issues over here. So if this were data that I would be investigating, I'd be looking at these mothers that had much lower birth weights than I anticipated in the model and trying to figure out what was going on with them. You can see that in the QQ norm plot. You can see that there's some problems at the edges of these plots right here, right? So you can see that that's a problem right there. I can do the same thing with the level 2 residuals. And it's okay, blah, blah, blah. And then I can take all of these guys and put them together in one graph. And we have a nice, pretty graph where I can look at my residuals and the normality of them. So level 2, I'm doing much better than I am at level 1. There's something going on here at level 1. And that can be lots of things. Like there's problems with births. There's sometimes mothers have problems. We don't know about, I imagine, a whole host of things about a pregnancy. So gestational diabetes, or whether there was some adverse health event or something like that would tell me something about the births and what the expected weight is. But there's some bursts that are just not captured very well by our model, and I would be interested in interrogate what that is. But overall, the residuals look fairly normally distributed. I wouldn't be particularly upset about that. And I would think that these would be pretty reasonable. Again, I would worry about those, but the normality of these residuals is pretty good, and we're pretty robust to those kinds of errors. So my point is that all of the tools you used for regular OLS regression are available here, including running robust standard errors. In Stata, we can run robust standard errors. So if we noticed heteroscedasticity by plotting these things, we could identify those. And when we get into class, I'll show it. But I want to try and keep these videos to under an hour. And here I am getting close to an hour. So I'm going to call that the end of this video. Thank you for listening, and I look forward to seeing you in class.